Hi and welcome to Maths class. So this is our second video on the fundamental theorem of calculus, and today in this video we're going to drill down into a little bit of theory. We're still not going too far, but really take the time to go through this video nice and slowly to give yourself a bit of an understanding of the theory behind the fundamental theorem of calculus. So first, just a reminder of what the fundamental theorem is. It's basically saying that if I find an antiderivative of this function f of x, and let's call that antiderivative g, then the definite integral from a to b of f of x is going to be found by calculating g of b minus g of a. And we're going to explore that now. So before we do, I'm going to go into a little bit of revision. Remember when we looked at left and right endpoint estimates? So what we did was we drew a rectangle under a graph. In fact, what we did was we drew several rectangles and added together all the areas in order to estimate the area under a graph over an interval. So I'm going to take that method now, and I'm going to place two points on my x-axis, this point x and this point x plus h, so the distance between them is h. And then I'm going to draw two rectangles. One will be my left point estimate, so the height of that rectangle is going to be f of x, and then the other is the right point estimate, the height of which will be f of x plus h. That means that I can find the area, which is the green area. Well, the width is h and the height is f of x, so it's h times f of x. And then this red area, which overlaps the green area a little bit, is the area of the larger triangle, the taller rectangle, which is f of x plus h times h. All right, the width is h and the height is f of x plus h. So this is small f of x plus h at this stage. So what that means is if I'm looking for the actual area under the curve, and I can see the curve kind of going through this little part of my rectangles there, if I want the actual area under the curve, it's going to be in between these. And as long as I've got an increasing function, then the left point estimate is going to be smaller than the actual area, and the right point estimate is going to be larger than the actual area. So now I'm going to use that in my next diagram. Okay, so change of direction here. Here's my function again, y equals f of x, and now I've placed 2 points on the x-axis, a and x, and I've shaded the area under the graph in between the 2 points a and x, and I'm going to define a new function, and I'm going to call that function capital F of x, and I'm going to say that it's a function which gives the area under the curve between a and x. But at the moment, I don't know any more than that. So I don't actually have an expression for this function yet. I don't yet know how it links to small f of x. All I know is I'm going to define this function, and somehow I'm going to figure out what that function is. All right, but the function gives the area. So I've added something new to my diagram. I've now put a point to the right of x, which is x plus h, and of course it's at a distance of h from x. And what I'm saying then is that what I know now, if capital F of x is defined as the function giving an area between a and x, then capital of x plus h must therefore be the area under the curve between a and x plus h. So in other words, from a to x plus h here, it's this whole area. I haven't shaded it, but I want you to see that it's this whole area. It incorporates this white strip as well as this red shaded strip. That's that whole area under the curve. Now what I'm going to do is I'm going to find myself an expression for that green shaded area that I've just newly shaded. So that's going to be in between x and x plus h. I can't call it capital F of x plus h because that's defined as the area from A. So what is the expression for this green shaded area? Well, it's going to be this f of x plus h minus f of x. So if I take this red shaded region away, I'm going to be left with this green strip. And so the shaded area, the green strip, is going to be f of x plus h minus f of x. So the green shaded area can be given with this expression, capital F of x plus h minus capital F of x. But if I go back to the diagram that we started with, I said that this shaded area, which is under the curve, is going to be smaller than the big rectangle. Oops, you can't see that. Smaller than the big rectangle and bigger than the small rectangle. So the actual area that we're talking about here is actually f of x plus h minus f of x. I don't know much about this at the moment, except that I know it's going to be more than h times f of x and less than h times f of x plus h. So now what I'm going to do is I'm simply going to divide everything there by h. Now I'm assuming h is a positive value because x plus h is to the right of x. So I can safely divide without needing to change any of my inequality signs. So if I divide right through by h, on the very left here I'll get f of x. And in the middle I'm going to get capital F of x plus h minus capital F of x all over h. And that's going to be less than, divide this by h, f of x plus h. Now, hopefully you've started to just go, oh, wait a minute, that looks familiar. This is a very familiar formula to us. Remember, this is just a bit of revision for you in case you can't remember why it's familiar. When I find a derivative from first principles, if I've got a function f of x, then the derivative of that function is defined as the limit as h approaches 0 of f of x plus h minus f of x over h. Of course, I don't have a limit as h approaches 0 in this formula. So what would it mean if I explored the limit as h approaches 0? It's going to mean I'm looking for an area of a rectangle, well, not a rectangle, a little space here under the curve that is, the width is infinitely small and the height is going to be approximately f of x. Now, why do I say it's approximately f of x? Well, let's write all this thinking down. As h approaches 0, what's going to happen to f of x plus h? It's actually going to approach f of x. Right? If I move this point really, really close to x, then the height, the two heights will be almost the same. Not exactly the same. H is not 0. So f of x plus h in a function with a positive slope will still be slightly taller than f of x, but not by a lot. So what that means is that this guy in the middle is going to get squeezed in between f of x and something that approaches f of x. So the limit as h approaches 0 of this expression is going to be f of x, because it's going to have f of x on it it's going to be more than f of x, and it's going to be less than something that approaches f of x. Now remember, the definition of a limit is the value that this will approach as h approaches 0. So it is going to approach f of x, therefore the limit equals f of x. Okay, go back to our derivative function. If I have a function f, then the derivative is this. That means that if I have this, then this function here is going to be the antiderivative. Okay, this part here correlates to this function f, this f of x. So if I just change these to capital F's, then this expression here is going to give me the derivative of capital F. So let's go back to this. This is going to be the derivative of capital F. In other words, this left-hand side of my equation is going to equal f dash of x. but I've just established that this is equal to f of x. So remember that capital F was a function which I originally defined as the area under the graph between a and x. What I've now shown is that the derivative of that function is f of x, which is the function of the curve that I'm talking about, which means, therefore, that f of x is an antiderivative of f of x. Let's put in a plus c. So remember again that f of x is the curve that I started with, and capital F I defined as the area under that curve between a and the point x. And so now I've added my plus c, but that's the integral expression that I've come up with. All right, so now I'm going to say what happens when x equals a. So I'm going to substitute a for x in here. So what I'm going to get then is f of a plus c. That's this and my plus c. But if x equals a on my graph, then that means x is literally sitting on top of a, which means there is no distance at all between a and x. So we know, therefore, that the area under the graph between a and a is going to be 0 because it will have no width at all. So I know that this equals 0, and I therefore can say c is equal to negative f of a. So I'm now going to rewrite this equation with c being negative f of a, the integral of f of x dx. And remember that what I'm really calculating is the area under the graph from a to x is going to be given by f of x minus f of a. And I've got one more step until we get our final result. And now I'm going to let x equal b. So the last step is when x equals b, I have the integral of f of x dx from a to b is f of b minus f of a, and that is the fundamental theorem of calculus that I was wanting to show you in the first place. Now we've used g here instead of f. Same thing. F of x was originally defined as the area under the curve, but I also know that it's the antiderivative of f of x. So that's the link between the function f of x, which is the area under the curve, and the antiderivative of f of x. Okay, that's the end of this video. There are no more worked examples for this one. The worked examples were on the previous video. So go over it, have a think about it, make sure that you understand all the concepts. Remember that mathematics is not just about applying numbers to a given formula. It's the mathematicians that came up with the formulas. So it's really important that we try to understand the process that shows us that this formula is correct. All right, that's the end of the video.